Okay, so today we'll take a second perspective on global spatial autocorrelation, one that's based on geostatistical perspective using the variogram as a device to summarize spatial autocorrelation. As we saw last week, with global measures of spatial autocorrelation, a single statistic like a Moran's I or a Geary C or a joint count statistic summarizes the pattern in the data. And it will be a similar approach here, but it's not a single statistic, it's actually a function. And it's a bit strange concept, but it'll all make sense at the end, I hope. It's very similar to the Covariogram, the non-parametric spatial Covariogram that we saw at the end of last week, which is, measuring how the strength of the spatial correlation changes with distance. So what we're going to do is first I'll step back a bit and give you a little more formal conceptual framework of where this all fits in. It's actually quite intriguing because it deals with how can we treat what is in essence a single observation, the pattern we observe, as multiple observations so we can do statistics. We can take means, variances, and stuff like that. Then we'll talk a little bit about different ways of measuring the semi-variogram, which is called variography. It comes from mining engineering originally. We'll revisit the Covariogram, but from a slightly different perspective. And then very briefly, I'll talk about theoretical models for the variogram. I say very briefly because this could easily be 1 or 2 quarters in its own right. It's a very large field. It has a lot of different applications, a lot of very tricky technical issues that there's just no way I can cover. So what I did for the readings, I gave you what I think is a very nice little and readable, which is not always the case for the literature in this field, overview of the geostatistical perspective. And then the additional materials are really geared to the R package GStat, which is one of the larger spatial statistical packages in R, dealing with various aspects of geostatistics, both cross-sectionally as well as space-time, both for a single variable as well as for multivariables. And we won't, we barely scratch the surface in what we use in GStat, but there's a nice little vignette that uses a data set in the Netherlands with various pollutants in it. And then there's the manual itself. And then in the Bivand et al. Book, there is a section that reviews this as well. This is a little more for R programmers. It's a little more technical. So let's start with this geostatistical perspective. And the formal concept is that of a spatial random field. And it's a spatial expression of a stochastic process. Now, what is a stochastic process? Is this kind of imaginary thing that generates observations. And the observations are not deterministic, so they're not always the same, but there is randomness embedded in this. But the randomness has a particular structure. That's why we can study it. If it didn't have any structure, we'd be lost. And so specifically, in the geostatistical perspective, we deal with spatial random fields. So processes, which are mathematical operations, that generate observations in 2 dimensions. So 2 dimensions in a space. And they're continuous. So it's not, like what we've done so far, discrete spatial units like census tracts or things like that, or points that represent the census tracts, or like the house sales points that we had before, but it's about a continuous surface, right? So formally, it's a collection, a set, the brackets signify a set, of random variables z tagged with a location s. And that location s is part of a domain. Now typically, and in our applications, that domain is two-dimensional, right? We just deal with 2 dimensions. But actually, the more fascinating and where the money is in geostatistics is 3D applications. As I mentioned earlier, this comes out of mining. Major applications are in petroleum exploration, where it's very expensive to do test drills. So what you try to do as an oil company is minimize the number of test drills and maximize the information that they give you. Information being, where is the oil, how much oil is there, and where should I drill to get the most out of it. So that's where the money is in geostatistics and in these mining applications. Of course, there are also, do-goodery sides to this, having to do with pollution. For example, if you have dioxin poisoning of the soil, how do you know how much is in there? Of course, you can't dig everything out. You have to do, again, same thing. You take samples and then figure out the volume, not so much the surface, but the volume in 3D. But the principle is the same. You think of it as a random variable with a location attribute, and the spatial index is either part of 2-dimension, 3-dimension. If you throw in time, it could be 4 dimensions. So it's very general. But the key differentiating factor between this and what we've done so far is that it's continuous. So conceptually, infinitely many locations where you can measure this random variable. Of course, we can't do that, and we have to work with observations at a finite number of sample points. So the observation set consists of sample locations at which we observe the random variable. And so then the challenge is, how can we, from these observations, estimate, fit the surface, figure out what is the process that generates the surface, right? So it's, again, a little bit of the inverse problem. We don't actually observe the process. We observe the pattern. How do we get to the process from the pattern? And so in this case, it's very concrete. Let's say we want to have a measure of air quality over the whole city. There's no way we can go around and measure air quality everywhere. We can put in a reasonable number of sensors, 20, 30, and treat these as sample points that give us observations at a number of locations S, from which we then infer what is the process that generated this. Now, there's a problem. And the big problem is that we really only have one observation. The pattern is the observation, n equal 1. In time series, it's the same thing. The single time series you observe is one observation. And why can you actually do statistics with that? By imposing structure, and we'll have to do that as well. So these are kind of examples. This is what we're going to use in the lab. The house prices, this is a very old data set, but it's very suitable for this. So we have different house prices, what we want to end up with, but we won't actually go that far in this course because it's only so much we can do, is a predicted surface. So in other words, if you want to know, there's a new location, what would be the house price at that location, your surface will predict it. Or if you have kind of this is a problem that I actually worked on. LA Basin, you have a 30-some monitoring stations. You have ozone, PM, 10, all that stuff. So if you're looking at house prices and you argue that environmental quality is somehow capitalized into the value of a house, then the house prices should somehow reflect that, right? And you put that, economists call this a hedonic model. You put the characteristics of the house in the equation, including air quality. Now, there is no sensor sitting on each house. So how do we get the air quality? We have to somehow, from the information on these measurement stations, figure out what is the surface of the air quality. And then if we have that surface, because it's continuous, at any location of a house, we stick in the XY coordinates and we have a predicted value or an interpolation of what the air quality might be at that house. So that's an example of how you use this, other than oil exploration. Okay, the conceptual, yeah.
How would you do that? Like, how could you ever make those assumptions about where it's continuous, the air quality?
Well, you get the assumptions from a model. There's two things, and I'm going to talk about it in a second. So one is a model for the average, for the mean. And that could be either a simple trend surface, which is a polynomial in the x and y coordinates, which you can always fit, right? Or it's combining that information with, say, remotely sensed information on the landscape, the vegetation index, the slope, the altitude, things like that. So then, in addition, you have the model that comes from the interpolation, which deals with the error terms. That's what this is about, okay? Because this is an impossible problem, right? You have one data point. How can you estimate a model for one data point? You can't. So we're going to, I'm not going to call it cheat, but be clever, right? And we're going to be clever by imposing structure on the process so that we can actually deal with the individual sensor points as if they were individual observations, not the 30 points together as one pattern, as one N, right? And the way we can do this is by imposing a notion of equilibrium, and we'll get there in a few times. So the think of it this way. Say the air quality is the same everywhere, right? The same, exact same. In a deterministic model, no random nothing, you would have a horizontal plane. There would be no deviation, right? Because it is a stochastic process, you can think of it as a constant plus a random error term, right? So even though, let's say, the air quality is 10 everywhere, if you have 30 measures, they won't all be 10. They will be 10 plus or minus whatever randomness the error process causes, right? But still, on average, you will get 10, right? So because it is the same everywhere, it shouldn't matter whether you see all 30 sensors or 5 of them or 10 of them or 5 of them here or 5 of them there. Okay. That's the notion of stationarity. That's the notion of equilibrium. Basically what we want to get at is formal assumptions that allow us to observe the process anywhere and at whatever scale, in a sense, whatever number of sensors, and we always get the same information. So whether you take, if you think of this class as sensors, whether I talk to these people or I talk to these people, I get exactly the same information. It doesn't matter where they are. Right? Now, obviously, if everything is constant everywhere, that will be the case. But that's not very interesting, right? And we'll get to the interesting part in a few minutes. So the key in this conceptual framework, and it's actually really tricky, it's really abstract to get your head around it, it's to be able to deal with the data points as if they were separate observations, whereas in fact they are not. And here's how we can do this, and I'm going to talk about it before I show you the formal notions. Think of this stochastic process as being the great number generator, and it generates not one number, but a whole surface, right? So all these surfaces are the same intrinsically. Let's say my example of a constant. They're all the same constant, but because of the randomness, they're all a little bit different, right? And let's say we are in control and we can generate 100 of these surfaces. And so because they're all basically the same, right? But because of the randomness, that's the only part that makes them actually different. So if they're all constant at 10, sometimes we may get 11, sometimes we may get 9.5, 9.75, but it's all 10 with the randomness, right? So let's say we generate one of these surfaces and we take a little subset, a little sample, and we figure out the mean, right? And then we generate another one and we take a little subset and we figure out the mean. Because it's the same process each time, the mean should be the same, right? So now think of your single map. Think of it as a map. It's the easiest. And let's say you have your first sensor, and you think of that sensor as being the observation generated the first time you generated the whole process, right? And the second sensor is the observation generated the second time you generated the whole process. So these are not now one data point. They're two different data points because they're each from a separate generation of the process. But since the process is the same, you can actually treat them as if they were two different data points. And that's the critical key in this, right? So as long as, just think of it as you have 30 monitoring stations. Think of it as 30 different generalizations of this process. The first station the first time, you ignore the other 29. The second station the second time, you ignore the other 29, and so on. And because we force this process to be the same every time, it doesn't really matter whether we look at 30 of these processes or we take one observation from the first one observation from the second one from the third one, and so on. So conceptually, we're back to square one, because now we can treat our 30 monitoring stations in our single cross-section. We don't have 30 maps, we have one, as if they were separate pieces of information that give us information about the process behind it. Now, the only way we can do this is if we assume that really this process is the same everywhere, because otherwise we're out to lunch, right? If there were two processes, one with a mean of 10, one with a mean of 20, we would have no way of figuring out which is which from our measurements, right? So we have to assume this incredibly strong notion of equilibrium, of stationarity. A stationary process is not interesting. So keep that in mind. At first sight, it seems, well, we're throwing everything out. We're forcing everything to be the same everywhere. That's not interesting. It's not. But we're throwing everything out except the one part where we're interested in the stochastic process that is functioning. And that's going to be the part that has to do with space, with spatial interaction, with spatial correlation. Okay? So, translated. Stationarity is way too general. Stationarity in a strict sense is that the process is the same everywhere, but the process that's really saying way too much, right? So to make it practical, we make it concrete in terms of what we call the moments of the distribution, so the characteristics of the distribution. To begin with the mean, constant mean. Constant mean is now very interesting, right? It means the temperature is the same everywhere. The pollution is the same everywhere. That's pretty much an unrealistic assumption, right? So how do we get around this? We get around this by formulating a model for the mean. So we have a model for on average, what the temperature would be. And we have that model for every potential location. That's why typically in this kind of work, you use transsurfaces, which are models in terms of the coordinates. So you have coordinates for any possible locations. Or you use information from satellite remote imagery, which is also typically covers the whole space. So you have information for every location. In the housing equivalent, let's say you have characteristics on all the houses in a city, and the assessor's office has that, the people who figure out the taxes, but not every house gets sold. So in any given time period, you have a sample of houses that sold with their sales prices and their characteristics. So that gives you a model of, on average, how the sales price should vary, and then you can use that model to predict the value, the assessed value of the houses that didn't sell, right? Now, the part that you don't control is the error term. And in any regression, the error term has mean 0. Now we're back in business. Now we have a random variable with a constant mean, 0. Right? So then the second assumption is constant variance. The variability has to be the same. If you think in terms of regression, that means no heteroscedasticity, homoscedasticity, constant variance of the error term throughout. So again, if you have heteroscedasticity, you have to deal with it. And you typically deal with it by transforming the variable or changing the functional form or some trick like that, right? And then the thing that we let vary is the covariance. But here, even here, we're putting restrictions on the covariance. The covariance doesn't matter where you measure it. What matters, it's about interaction, right? So what matters is the distance between the pairs for which you measure the covariance. Covariance is always 2. And this is autocovariance, so it's the same variable at 2 locations. So in other words, the covariance becomes a function of the distance that separates the 2 locations and only the distance. So again, whether you look here 10 miles apart or you look there 10 miles apart, it's the 10 miles that matter, not whether you're east or west. Right? So now we're in business. Now we're going to relate the covariance to the distance of the pairs of observations that separates them. Now, what is this going to give us? At the end of the day, it is going to give us better predictions, but not better predictions in a traditional, biased, unbiased sense, but better predictions in a precision sense. Because, and this is a classic article by Arthur Goldberger, we will exploit the structure of the error covariance. So because error terms are supposed to be noise, right? There's not supposed to be any rhyme or reason to them. No systematic trends, the mean is 0. No different variability, variance is constant. No correlation, right? When there is structure, you can ignore it, and on average, you're on target, you're unbiased, but your precision may not be very good. And by exploiting the structure of this covariance, in our case, spatial covariance, we will be able to get better predictions, better in a sense of higher precision, because you're exploiting some structure in what should be noise. It's not noise. You can act as if it's noise, and on average, because they all wash out, you're still on target, but your precision won't be as good as if you take advantage of knowledge of the structure of the covariance. That's what it's all about in geostatistics. So what we're going to do first, and mostly because we only have so much time, is try to understand how does this covariance change with distance, and what kind of structure does that give us, and ultimately, in contrast to what we did last week where we let it be fit non-parametrically, we'll fit a model to it, a particular function to this change in covariance or correlation, if you wish, with the distance of separation. And the key concept, and it's a bit of a weird one, a lot of this literature is kind of weird. It doesn't come from statistics. It comes from mining engineering. So it's only fairly recently, actually, I mean, basically since the late 80s, early 90s, that mainstream statistics has kind of adopted this in spatial statistics and put a more formal mathematical statistical framework around it as stochastic processes. But a lot of the terminology, and we'll see some later on towards the end, a lot of the terminology comes from very practical mining applications where you don't care about the stochastic process, but you want to get it right, how much gold there is in that mountain. That's basically, a lot of this comes from South African gold mining. So there's this thing called the intrinsic hypothesis, and it's actually, I find it a very strange concept, and it's a little difficult to get your head around it, but at the end of the day, you will see it all kind of simplifies. So we take stationarity in the mean, so constant mean, and constant variance. That in practice, this implies that we have some kind of model for the mean, and if necessary, also kind of a model for the variance. So then what's left is this randomness that has some structure, but not too much, right? And the structure is that, and this is a mouthful, and you have to think about what this really means. So the variance of the first difference is only a function of displacement or of the separating distance. So it's not the mean, because the mean is constant. That's not interesting. It's not the variance, because the variance is also constant. That's not interesting. But it's the variability of the difference between two observations that are a given distance apart. The variability. It's all about the second moment, not the first moment. Because on average, what is this difference between two observations that are h, distance h apart? Remember what we assume up there. The mean is the same. So what is the mean of the difference? 0, right? So that's not an interesting magnitude, right? But because these are variances, they are not 0. And so how do these variances change with the distance that separates these observations? So the variance of the difference as a function of h, the displacement. And here's a bit of a weird thing, but you'll see why this is happening. So the proper technical term is the semi-variogram. And the semi-variogram is half the variogram. So the variogram is twice the semi-variogram. And we'll see later in a few slides why that actually makes sense, right? So it's not, it typically is represented as gamma. It's not gamma h that is the variance of the difference separated by distance h, but it's 2 gamma h. So then the semi-variogram is 1/2 of this. Now, you know, whether you take 1/2 or the whole thing, it doesn't really matter. It does matter when you use software that you know what it is that they're giving you. Because some software will give you the variogram, some software will give you the semi-variogram. One will be double of the other, right? So as long as you know which is which, you're fine. But it is a convention. So what is this thing actually, if we look at it a little more operationally? So first of all, as we already said, we have this constant mean assumption. So if we look to the expected value on average, what is the difference between these two random variables? Since their expected values are the same, the difference is 0. Right? And then we go back to the fundamental equation of what is a variance. So the variance of the difference between these two random variables is the expected value of their square, minus the square of their expected value. And their expected value we just saw is 0. So the only thing that matters is this first term, is the expected value of the square. So then for all practical purposes, the semi-variogram, gamma h, is 1/2 the expected value of the square difference. And now we're in business because we're good with expected values. We estimate those as averages, right? An expected value is estimated as the mean or the average in real observations. So we will estimate the semi-variogram as some kind of average of square differences for a given distance interval, right? So if we look at, it's about pairs. It's about, you know, double the data set, so to speak, of the order of magnitude of n squared, right? So we have every observation, and every observation relative to every other observation is a given distance apart. For any given distance, we will take the average of the square difference of the variables that we observe. What's the catch? This is the catch. So this is what this looks like. So on the horizontal axis, we have all the distances. On the vertical axis, we have the square differences. So how do you get the square differences for each distance?
Are you implicitly binning, or are you not? Are you computing this based on a single observation? Because distance is continuous, so there's only one observation for everyone.
Perfect. That's just what I was going to say. Because that is the catch. You know, distance is continuous, so there is no way you can compute an average unless somehow, by great chance and with great precision, you would have multiple pairs that are exactly the same distance apart. Okay? So conceptually, it is a function, a continuous function of distance. In practice, we will bin the way we did before when we did the Covariogram. So this variogram cloud plot gives you everything. And so for estimation purposes, we just established it's not really that useful, even though you could fit a curve through it. But it is useful to explore and identify outliers. And outliers in the following sense. So this is squared difference, right? And we're dealing with spatial autocorrelation. So the closer the observations are, the more spatially correlated they are, the smaller their square difference should be. So the square difference should go up with distance. The Tobler's law, the further apart, the more different they are, so the larger the square difference will be. Right? So what we get here, we have everything. These are all the pairs. When we start looking at so this is distance, and this is the semi-variance, so basically half the square difference between them. And so we start seeing points like these that are not very far apart, but are very different. So the vertical axis is a measure of the difference between the pairs. So every one of these dots is 2 observations, right? Not 1 observation. It's 2 observations because it's the square half the square difference between the values observed at 2 points that are this distance apart. So if we see points that are, in a sense, close in space, but very different in terms of attribute space, something's not right. Right? And we call those outliers. And there's in the Baltimore house prices, it's, you know, it's not actually that interesting, but in R you can interact with the graph and you can click on these. You see every one of these is 2 observations, There's two numbers here. And then you can see where they are on the plot. And for example, if you look up there, you see a big circle and a little circle that are very close together. So that shouldn't happen. You know, all the big circles should be close together and all the little circles should be close together. In an example that I used to use, I'm looking at air pollution in LA. It's always the same thing. There is a very interesting phenomenon in LA. LA is a basin, right? And as you move up to the edge of the basin near the mountains, going eastward, the air quality gets really bad, you know. But then when you go over the ridge, it gets better again. As it happens, there are two monitoring stations that are on each side of the ridge. So these are close together, but they measure very different phenomena, because one measures, in essence, the pollution inside the basin, and the other one measures the pollution outside the basin. So if you're just looking at this, you know, the counterpart of this for the LA data, I mean, it just jumps at you. You have all these high points, and you click on them, and they're all connected to the same outlier. The same station across the ridge is close to the stations on the inside and very different in terms of measurement. And so then the question is, if we're trying to estimate a surface and we have this one measurement station that gives us very different measures, should we keep it in or kick it out? Okay, that's always the decision you have to make with outliers. Do you keep them in or do you kick them out, right? And there's pros and cons. It really depends on what you're trying to do. The key notion is that you have to acknowledge their existence. Don't act as if they're not there, because it's going to goof up your analysis. You know. Okay. So then, as we established, you can't do anything with this variogram cloud. We have to estimate what is called the empirical variogram. And the empirical variogram is very similar to what we've already done with the non-parametric spatial correlogram. We bin the pairs, then we, so we could take the whole cloud plot, but we're not going to do this. So some software does this. It's not recommended, you know. But we do this, and it's really technically a method of moments estimator, where you estimate the variogram by the average of the square difference for all the observations in a given bin. So it's the same rationale as what we've done before. We bin the pairs by distance bands. In each bin, we have NH pairs. So we sum all the square differences and divide it by the number of pairs, and that's our measure of the variogram, or 1/2 of that is our measure of the semi-variogram. You know. So it's very simple. In fact, it's very similar to what we've done so far with the correlation. In the correlation, we took the cross products. Here we take the square differences. Pardon? Well, we'll get there. But you have to have a function for the line. What's your function going to be? Yeah, yeah. You have to, so that's where we're going. We need a model, because you can't just fit a line through it, because there's this notion, remember Tobler's law. The implication of it is if you move far enough apart, and we've already seen this with the correlogram, then there's no more correlation, right? So at some point, if you think of the empirical variogram as being very small for very short distances, as the distance increases, it goes up. And then as it reaches a certain, we'll call it the range, beyond that, it doesn't really matter anymore. There's no effective distance anymore, and then it's flat. So we'll have to have a functional form that respects that. So a line is not going to work, because the line keeps going up, or you know, wouldn't reflect this leveling off of the function. Right? But that's actually is what we're going to do. But the question is, how are we going to fit this function to these data points? Do we use all of them? And we can, but it's not very stable for a number of reasons. Or do we go to our binning situation, which is not ideal either, but it's better. It's not ideal because the precision of this estimate, you know, this is an average. So the precision of the average depends on how many data points go into it, right? And this is our rule of thumb that we kind of loosely talked about, having at least 30 in every bin.
Why not use a kernel here?
You can, but then you don't have your functional form. So it's a trade-off between the non-parametric and the parametric. The one reason why you might not use a kernel would be that you need, and it's kind of difficult to grasp this, but it's this notion of not having negative variances, right? And so the function that comes from the kernel has to yield a variance covariance matrix that's positive definite, which the kernel as such does not guarantee. And these functions, these quote-unquote approved functions in geostatistics do guarantee that. That's the main thing. But yes, from an exploratory point of view, there is no difference. So there's all these practical issues. We already talked about this before in the context of the Covariogram. What is the maximum distance that we bin to, right? So at some point, the information about the square differences is really not very relevant because the pairs are too far apart and it doesn't tell us anything about the sloping of the curve. Basically, what we're interested in is figuring out, you know, how fast does this curve go up and at what point, that's the range, does it flatten out. So if you think of this as a curve that goes up and then is horizontal, we're really not very interested in the horizontal part. You know, once we know where it flips to horizontal, you know, we don't really care about the observation points at the very tail of that horizontal line. So typically we exclude a bunch of distances in this process, which is what I talked about a little bit in the lab with the Covariogram, right? The cutoff distance. So what is this cutoff distance? And there are a bunch of rules of thumb in the literature. My favorite is trial and error, which is not on the list, but that's how you find out how sensitive your results are to different choices. But the default in some packages, and you should check that out, you should figure out what it is that they use, is half the maximum distance. But since there's often, you know, real outliers in especially if you very irregular points, sometimes GStat, for example, which we'll use in the lab, takes 1/3 of the diagonal of the bounding box. So the bounding box is the rectangle that connects the lower right point and the upper left point. I mean, or the other way around, the ones that are the most extreme, that rectangle is the bounding box. So then you take the diagonal of that rectangle and take 1/3 of that. That is a rule of thumb for what is called the distance of reliability. And then one that will often bite you, especially with smaller data sets like the LA 30 monitoring stations, is that your bin width has to be such that you have enough observations in it. And if you're not careful with the software like GStat, with their defaults, you can get very strange situations. Like the default in GStat is that it takes your cutoff distance and then divides it by 15 to get the bin width. You know, but that could be too narrow a bin so that you end up with, say, 5 observations or 7 observations in one. Typically, that it happens at the very short end because there are not that many observations necessarily at the very shortest distances. So then you get very weird looking variograms because the average is based on insufficient information. You know, there is no averaging out, so to speak. It's much too sensitive to the particular values that you have. So this is something that we'll play around with in the lab, is figuring out what the proper bin is. And basically this estimate, even though it's a point estimate, is heteroscedastic. The precision of the point estimate depends on the number of pairs in the bin. If that number of pairs is not constant throughout all the bins, then the precision will not be the same in each bin. And so that's an additional statistical twist that you can take care of by robustifying the estimation, or you can ignore, but it's there, right? Anytime your number of pairs varies considerably between the bins, you're going to have problems of comparison, because one of these point estimates will be better than another one. And so even though, let's say, one is 10 and the other one is 15, the 10 may be 10 plus or minus 1, whereas the 15 may be 15 plus or minus 6. So in the end, you know, they're very difficult to compare, and that will affect your curve fitting at the end. So this is what this looks like. It is a typical example. These are the Baltimore house prices. This is the kind of graph that you get in GStat. It gives you, or it can give you, the number of observation pairs used to get that estimate in the table that's listed under NP. And you see, once we get to 7, it's really not going to matter that much, because they're all over 1,000. So then, even though strictly speaking the variances will be different, for all practical purposes they won't be that different. But there is a huge difference between 1,000 pairs and 60 pairs. So the precision of the first point estimate will be much worse than the precision of the estimates further on. This is no good. Why is this no good? I mean, it's fine. This is proper application. But why is this no good as a model for spatial autocorrelation? Because it never goes down. It just keeps going up. And that is, and you can show this mathematically. I won't do this here, but this has to do with a violation of the assumption of constant mean. And in the literature, this is called a trend, a spatial trend in the data. In other words, there is systematic variation of the mean. The mean is not constant. So how do we get the mean to be constant? We fit some kind of function to it so that the residual, by definition, has a constant mean of 0. So then we do the analysis not on the original variable, but on the residual of a regression model. Now, the difficulty is this is all fine in principle. The difficulty is when you move from fitting the model and estimating the model to spatial prediction. Spatial prediction is, in essence, finding values for locations for which you don't have any observations. So if you don't have any observations for the dependent variable, you very likely won't have any observations for the explanatory variables either. Right? So this only works in a situation where you do have observations on the right-hand side of the equation. Otherwise, you cannot predict the mean at the locations that you do not observe, right? If you could, if you assume a constant mean, you don't have to worry about that. But clearly in this case, and in many cases in practice, constant mean is not a realistic assumption, nor is it an interesting situation to study, right? If everything is the same everywhere, why bother, right? So you want to capture the variability in the mean first by means of a regression model. And ideally, that is a regression model with explanatory variables in it that you can observe everywhere. That is why a trend surface is so popular. X, Y coordinates you have for every point anywhere, right? When you go into more substantive things, then it gets trickier. Like in the house example, you would need assessor's data. That will give you square footage, number of bedrooms, number of bathrooms, those kind of characteristics. And hopefully they give you a good enough prediction of the variable of interest that the residual is an interesting residual that you can then use to model the spatial process for, right? So typically this is how you proceed. You start with the variable, usually you're out of luck and it just keeps going up. So then you fit a trend surface or something else to it, and you look at the residuals. And then hopefully at some point you end up with something that starts to flatten out at the larger distances. But flatten out is relative, you know, because it's not exactly. First of all, we just talked about the lack of constant precision, so there's going to be variability no matter what. So even though they're not exactly on a horizontal line, if they're more or less suggesting some flattening out, that's good enough, right? And this is called the empirical variogram. Empirical because it's estimated from the data. It's not a model. Next, and in a few minutes, we'll move to the variogram model, which is an actual equation that we fit to the data points. Okay, so we've already been through this in the context of the Covariogram. We can change the cutoff distance. We can, because basically all the action is in the shortest distances. You know, Tobler's law, decay. As you go further away, there's no more correlation. It's not interested from our point of view. And so the larger distances, as I mentioned, they tend not to be correlated, so why even think of them? But also, because of the nature of the density of the points, there tend to be fewer pairs of them. Fewer pairs are really large distances away from each other. It really thins out as you move up. So this is the kind of thing we'll do in the lab, you know, change the cutoff distance, see if it's a little nicer flattening surface. And okay, one more thing. So far we have our moment stationarity, constant mean, constant variance, the square difference, the variability of the difference only changes with distance. That's the assumption of what is called an isotropic plane, or as I like to call it, a pancake. Well, a well-made pancake, right? Everything is the same in all directions. No difference. The only thing that matters is distance. Now, oftentimes in phenomena, in reality, that's not really the case. And for example, in air pollution studies, there is often, especially in a coastal city like LA, the effect of wind direction. So if the effect of wind direction matters, then not only is it important to know how far two observation points are from each other, but also how they are oriented. Are they like 45 degree, or are they, you know, 0 degree horizontal in a 2D map, or are they one above the other? If there's wind direction effects, that's going to matter. If the predominant prevailing wind is from the west, then the effects in the western direction will be different from the effects in the eastern direction. So how we do this is by means of a so-called directional variogram. And basically what a directional variogram does is cut the space up not only in terms of distance bins, but distance and angle bins. So you say 0 to 10 miles, 0 to 45 degrees, right? Or something like that. Then 45 to 135, and so on. So you take both the relative positioning in terms of the angle between the 2 points as well as their distance. And typically you do this in 45-degree segments, and then you only have to do half of them because the space flips around. So if you flip the space around, the 180 to 360 will be exactly the same as 0 to 180. So you go 0 to 45, 45 to 90, and so on. So you look at these different classifications, and then so we have a double binning, right? On the horizontal axis, we have the binning by distance, just like we did before, and then the 4 quadrants are binning by angular direction. So this contains all the points that are this distance apart from each other, but also within a 45-degree angle from each other, right? And then the second one goes from 45 to 90. This goes from 90 to 135. That goes from 135 to 180. And that has all the different relative positionings. So what you want to see, if, well, depends on your point of view, but if you want to be lazy, what you want to see is that these empirical variograms are the same in all four quadrants. Because that means that then, in fact, you have an isotropic process. It is the same in all directions. You don't have to worry about it, right? If you want to get fancy, what you want to see is that these processes are very different depending on the angle of separation. For example, if you have a strong prevailing wind effect, or if you have some other situations might have to do with the slope of the mountain that you might be on, or things like that, right? So that anything, I mean, typically we look at angles because it's easy to do geometrically, but conceptually, anything that changes this uniform effect with distance only is a source of non-isotropy, right? And the approach is always the same. If we identify something that changes that shouldn't change, we structure it. So that then within the structure, again, it doesn't change anymore. So what we have done here, we said, well, conceptually, there could be a directional effect. Okay, let's bin these by direction. And then within each bin, the only thing that matters is distance. So it's the same logic. After a while, you know, you get used to it. You know, you start with something that's very messy. You put some structure on it. Then the remainder, the residual, shouldn't be messy. If the residual is still messy, then you put some more structure on it and just keep pushing it out and keep pushing it out till you're left with something where you can handle the randomness, right? So that's what we're doing here. There's another way of looking at the variogram, which is yet a more detailed way of binning. So in this directional variogram, we binned with big categories of angles, right? Now we can push this further and say, okay, 0 to 10, 10 to 20, 20 to 30, right? And that gives us then this thing that is called a variogram map. So we have a double binning in here. We have a binning in terms of distance, and then a binning in terms of angle. So each of these little squares corresponds to a combination distance separation, angular separation. So if the process is isotropic, meaning it's the same in all directions, what you like to see is a nice concentric pattern. You know, it's concentric because the only thing that matters is distance. As the distance becomes larger, the differences will become larger. And it should be the same in all directions. When you see systematic kind of slanted things like here, more or less, that might point to directional effects. And then in each specific case, you know, you have to decide what to do about that. But ideally, again, as I said, if you want to be lazy, you want to see nice concentric patterns in this variogram map. No, actually, you subset the whole data. I mean, everything is for the whole data set, but you're binning, right? So in the classic variogram, you bin by distance only. So you take all the pairs and you put them in distance bins, right? Here you put them in even smaller bins, because you can think of it as in each distance bin, you subset by possible direction. So it's like a double classification, right? It's the distance of separation in the horizontal direction and in the vertical direction. And that's why you get this kind of map. The horizontal distance is the horizontal, the vertical distance is the vertical. So the combination of these two gives you distance of separation and angle.
Oh, so it's not distance versus angle.
No, sorry. Yeah.
Two questions. One is, so, I mean, you're already having like really small beams with small distances. Like if you're adding these extra layers, like, aren't you concerned about like having too few data points?
Yes.
The other one is like, what to do to control for this factor one?
This. You kick him out. Okay. So if there are too few observations, the rule of thumb is 30, but it doesn't have to be 30. You kick him out. And of course, you know, this could be really bad, right? I mean, if you have too many of these, then you don't see a pattern at all. And that's, you know, the life of an empirical scientist. You know, the data is what it is. If it helps you, it's great. If it doesn't, back to the drawing board. Yeah. But that's exactly the point. This is a much finer classification, so as a result, there will be fewer pairs, and in fact, there might be not enough. So just like with the binning in the standard variogram, you want to make sure you have enough pairs in each bin. Here, because it's a double classification, it's even worse. Right? Okay, so now we move quickly to the Covariogram. This is, and then I'll move to the theoretical models. So the Covariogram is, I mean, and this is very subtle, right? So because so far with the variogram, the only assumptions we made were on the variance of the difference. That's actually a very robust way of dealing with the processes. It imposes relatively little structure because there are differences, there are square differences, right? When you get to the covariance, you have products. And products are trickier, are more demanding in a sense. I mean, it's hard to give you an intuition for this, but the assumptions needed for proper statistical inference are stronger for products than they are for square differences. Right? With the square difference, the mean washes out. Right? With the product, it doesn't. Right? That's kind of one way of thinking about it. So we've already talked about this when we talked about the Covariograms. It's a notion of covariance over space. So everything is the same, except now we take the cross product instead of the square differences. And of course, cross product at 0 distance is product with yourself, and that's the variance. So in the notation, the covariance at 0 distance is the variance of the process, and the covariance at distance h is the covariance at distance h, right? And now all of this comes very nicely together. So we can talk about the Covariogram. We've already done this. I'll skip this, and you know what it looks like, but this is the key thing. Is this just very simple algebra, but then the result is very nice, because the result gives a connection between the semi-variogram and the covariogram. We tend to be very uncomfortable with semi-variograms because it's kind of a weird thing, these squares. But we are very comfortable with covariograms, and we're definitely comfortable with variance, right? So if you do a little algebra and you look at the expected value of the square difference, right, that's the expected value of the square of the first one minus twice the expected value of the cross product plus the expected value of the squared of the second one. And so the mean is 0, doesn't matter, or it's irrelevant because it's constant. But also we've assumed that the variances are the same. So the expected value of the square of the first one and the expected value of the square of the second one are the same. They're the variance of the process. So you add them up, you have twice the variance of the process minus, very important, minus twice the covariance. And here's where the beauty of the semi-variogram comes in, because the variogram is twice this, right? So if you divide it by 2, you get rid of these funky 2's on the right-hand side, and we have this clean relationship between the semi-variance, the variance of the process, and the covariance at a given distance. Okay. Now, think of what this really means, right? So the covariance at small distances will be large or small? Large, right? That's the whole point. Closer, more related, right? So at small distances, you take the variance of the process, which is constant. That doesn't change. By assumption, it's constant. And you subtract a fairly large number from that. So that gives you a small number. As the distance increases, right, the covariance that you subtract gets smaller. So the semi-variance gets larger. So these two are like duals of each other in the economic sense, right? Two sides of the same coin. So you look at the semi-variogram, it goes up with distance, and at some point it is flat, equal to the variance of the process. Because at some point, for all practical purposes, the covariance will be 0. So what you end up with is semi-variance equal C0, equal the variance of the process, right? And the covariance starts high at small distances, but then as h increases, the covariance becomes 0. So they're flip sides of the same phenomenon, which is the distance decay phenomenon, which is closer things are more dependent than things that are further apart. So this is the equation that ties it all together. So then the models, weird stuff. I told you it comes from engineering. These terms have been around forever, and they tend to be related to golden nuggets and things like that, but don't really have much connection with statistical terminology. The process variance, the C0 that we just talked about, is called the SIL of the process, of the spatial process. The range, we've already talked about the range before, is the distance beyond there is no more spatial autocorrelation. That's the same in the Covariogram as it is in the Variogram. And then the nugget is a real nugget, right? The nugget is something that shouldn't exist, but it does. So at distance 0, there should be nothing, right? The whole process, the function, should start at 0, 0. At 0, 0, no semi-variance, right? But then the moment we go a little bit larger than 0, there is semi-variance. So in practice, we have a problem, right? Because we're looking at the square distances between points that are a given distance apart, and we don't really look at what happens in the distance range that is smaller than the smallest nearest neighbor distance. If the closest 2 points are 5 miles apart, we don't know anything about what happens at 4, 3, 2, 1 mile. We simply don't have any observation. So part of this nugget effect is measurement error. Part of it is also microscale variability. That's where the term nugget comes from. Literally, it was a nugget of gold, a clump of gold, which has more gold than the stuff around it, right? And so it's at the very micro scale, but it is variability. It doesn't fit the rest of the process. So this is what one of these theoretical variograms looks like. It should start at 0, 0. It kind of gradually curves until it hits the range. And beyond the range, there is no more spatial autocorrelation. So at that point, the semi-variogram equals the variance of the process. At that point, gamma h equals C0. Before, gamma h equals C0 minus CH, right? And CH is very large for short distances. So as you move on, CH gets smaller, so the curve goes up. Okay. So what do these things mean more formally? The SIL is really the variance of the process, as I mentioned. So just to recap, we have our equation that ties everything together. As h goes to infinity, but it doesn't, it's typically not infinity, then the covariance for h goes to 0. So the remainder, the semi-variance, goes to the variance of the process. So that's the variance. The total variance of the process is actually the height of this curve once it's flat. Okay. Then the range, we talked about that too. It's where it flattens out. So the range is that h, that value for h, for which the semi-variogram at h equals the variance of the process. So it's kind of flipping it around. You know, solve for distance the point where the curve becomes flat, where the slope of the curve becomes 0. You know, what is that h? If you have the curve as a function of distance, you get it first partial derivative and solve it. That is the range, right? For those of you who like to do that kind of stuff. The important implication of this, and we talked about this already in the context of the Covariogram, is that if you're interested in designing a spatial sample where the sample points are not spatially correlated, you make sure they're further than the range apart. So how you can do this is you take, for example, if you're looking at remotely sensed images, which are thousands of pixels, you take a subset of the pixels, you fit these kind of models to them, you figure out what the range is, and then you resample the pixels. But if you're not interested in spatial autocorrelation, you make sure that they're far enough apart. And that gives you then a clean, uncorrelated sample where you can use all the usual statistics, not having to worry about spatial autocorrelation. Okay. The nugget is the weird one, is where the semi-variogram should be 0 at the origin by definition, but empirically, so when you fit a curve to these empirical variogram points, you sometimes get an intercept that is not 0, 0. That's the nugget. So then we call its microscale variation is the gold nugget, or its measurement ever more likely. This means that things in terms of terminology get a little complicated because we know where the sill is. The sill is the variance of the process, right? But then we also have some variance at 0, which is this nugget thing. So then we have the difference between the sill and the nugget, and that is called the partial sill. And the reason why that is relevant is that some of the models, as we'll see in a minute, we have a minute, use this partial sill in the model specification. Not the sill itself, but the partial sill. So they use the nugget, which you can think of as an intercept, and then the sill, which is the top, and the difference between the sill and the nugget is the partial sill, right? So if you have the nugget and the partial sill, you get the sill by adding them up. If you have the nugget and the sill, you get the partial sill by subtracting the nugget. So 2 out of the 3, you know the third one. Okay. The key issue I already mentioned is why not use non-parametrics, is they don't guarantee that your covariance function is positive definite. This we already saw with the Covariogram. But for the semi-variance, since it's kind of the flip side, it has to be negative definite. So this yields in the literature, and is a huge literature, valid parametric models. Valid both in terms of functional form as well in terms of parameter space to guarantee that you end up with something that doesn't give you weird covariance matrices. So these are some examples of these valid models. The spherical one is the most commonly used one. Exponential, Gaussian, waveform. They can get very fancy and incorporate all kinds of weird shapes with different parameters. I just want you to know this exists. It's out there. We don't have time to talk about it. I do want to show you, to close, the spherical variogram and how all these things kind of tie together. So the spherical variogram is, or I should say semi-variogram. to be precise, is kind of a double equation. So for distances that are beyond the range, and the range is a parameter, so we have to estimate the range, it's a constant, right? And the constant is the nugget plus the partial sill. That's why the partial sill is here. And so then the sill, the variance of the process, is the sum of these two parameters, right? And then as we get to the flat part, this curvature is modeled by this equation. So for any distance before we get to the range, we have kind of an intercept, if you wish, and then a slope, which is the partial sill, and then this function of the distance relative to the range. As you get closer to the range, then the curvature changes. So these are the three parameters. And then in practice, you need to fit this. You fit this to the estimates from the empirical variogram. There's also other ways of fitting this, as I point out here at the bottom. Many technical issues, and I'm not kidding you, right? There's whole books written on how to do this, right? And not just for continuous variable, but for count variables, for 0, 1 variables. It is space-time, cross covariograms with multiple variables, and so on. So the way this is done in practice is kind of weird, actually. It's a nonlinear fit, nonlinear model fit, but you have to give it good starting values. And it's very sensitive to the starting values. So if you throw in 0, 0, 0, it doesn't work, right? And so that's because there are not very many data points, right? Unlike, you know, when you typically fit nonlinear models, you have 10,000 observations or something in that range, right? Here we're going to have 15, right? 15 bins for our empirical variogram. So we're fitting a nonlinear function to 15 observations. That's not that easy to do automatically, right? So it's critical in practice to start with good starting values. And that's a bit of an art. And you got to get good at it. So you can fit it to the cloud, but that's typically very unreliable. But typically this is what you do. So you figure out the empirical variogram till you get one that is nice and flattening out somehow. Then you give it some starting values for the intercept, which is the nugget, the partial sill, which is the difference between the intercept and where it goes horizontal. And then the range is where you kind of eyeball it, that it goes horizontal. You fit these starting values into a nonlinear optimization program that comes out with a bunch of final parameters, as well as a measure, a fit, a sum of squared errors. And that becomes then the tool that you use in spatial prediction. Spatial prediction, unfortunately, I don't have time to talk about, but that is the ultimate goal of all of this. Okay? So that's it.